So what I'm going to do here in this video is go through some examples of cells, applying what we have just learned to actual cells that are used in industry. So the first one, which I'm quite sure we're all familiar with, is a common battery that you can buy in any stores that you would use in, devices like your remote control for your TVs and so on. And again, it's all based on what we have just learned. You have a redox reaction taking place where oxidation takes place at the anode and reduction takes place at the cathode. Now, the materials here are a bit more complicated than the ones that we have looked at, but the underlying principle is still the same. And this is called a dry cell, also known as a Leclanche cell. And as you can see here, the oxidation reaction is where the zinc is undergoing oxidation to form the zinc 2+ ion, and that's a zinc anode right here. Okay, that's where the oxidation takes place. And then in the cathode, you have this reduction reaction takes place where the ammonium, which is from the paste here, which is made up of zinc chloride and ammonium chloride, the ammonium ion undergoes oxidation, or I should say reduction, with manganese 4 oxide, which is in a layer, this blue part right here, that's the manganese oxide. So that's the reaction taking place here. And of course, as always, you can determine what the overall equation is by adding those two together, and you're going to get this reaction here. So this is basically the reaction that is taking place in this type of cell. All right. Here's another one. Now this one is known as a mercury battery, and you'll be seeing these types being used in other devices like calculators and watches and so on. And again, same underlying principle. Oxidation takes place at the anode, reduction takes place at the cathode, and these are the corresponding equations right here. And when you add these two together, you get the net equation. So this is the overall reaction here that is taking place when it comes to the mercury battery. And it is, of course, recommended that you don't discard these in the normal trash because this produces mercury, which, of course, can be harmful to the environment. So that's basically the mercury battery, how it works. All right. And then we get to our car batteries. All right. And again, same underlying principle. Now, in this case, it is the lead, which is basically undergoing oxidation in the presence of the sulfate ions. Now, the sulfate ions is usually produced by sulfuric acid, right? So the sulfuric acid produces sulfate ions, which reacts with the lead, and this is the oxidation reaction which takes place at the anode. And then at the cathode, you would have the reduction reaction taking place where lead 4 oxide is reduced to form lead 2 sulfate. All right. And again, you can add these two equations together to get the overall reaction. All right. So that's yet another example of a battery using an electrochemical reaction to form or produce electrical energy. And then we have the lithium, the solid state lithium battery. Now this one is a bit unique because, as stated here, it's solid state. So there's no solutions or aqueous environments involved because you have a solid electrolyte right here, which basically contains the lithium ion, or allows the lithium ion to be migrating towards the cathode. Now the way this works is that the lithium ion here, or the lithium electrode, is the anode, and therefore it undergoes oxidation to form the lithium ion. And the electrons, of course, will go into the external circuit and then end up at the cathode. And at the cathode, it is made up of this material right here, which is titanium 4 sulfide. And that undergoes reduction as seen in this equation right here. So that's basically how this works. And then we have this one, and the last I heard about this is that this is still something that scientists are still working on, to get a better device that can be used. It's called a fuel cell, which basically allows for this overall reaction to take place, the reaction between hydrogen and oxygen to form water, right? So people are working on this because the waste that is produced is harmless, basically H2O, all right? So, you don't have any dangerous pollutants involved when it comes to this sort of reaction taking place. So the way this works is that it requires a hot potassium hydroxide solution. The hydrogen is allowed to enter here, the oxygen enters here, and these two electrodes is basically made up of carbon, but it contains some other substances. In this case, in the case of the anode, it contains nickel. In the case of the cathode, it contains nickel and nickel 2 oxide. So the way this works is that the oxidation takes place here, of course, because this is the anode, and this is the equation for that reaction. As you can see, electrons are being lost, and those electrons will go into the external circuit, end up in the cathode, and at the cathode, reduction will take place, and this would be the reduction reaction right here. So these are the reactions here, which when added gives you the reaction where hydrogen and oxygen forms water. All right. As far as drawbacks to this is concerned, and I think this is what the scientists are working on, and that is that the fuel cell requires a continuous supply of reactants. So basically, you need a continuous supply of hydrogen and oxygen in order for this reaction to take place. In addition, you need a hot solution of potassium hydroxide in this device, right? So I think those are the drawbacks that people are working on in terms of making this a more convenient device that you can use for powering, anything that needs energy, even motor cars, all right? So that's basically what is involved in the fuel cell. Now, another application of what we have just learned in terms of electrochemical reactions that are spontaneously occurring is in this whole idea of protecting iron against corrosion. So we need to understand the reactions that are taking place when iron is undergoing corrosion. So iron, as I'm quite sure you all know, if left exposed to the atmosphere and to moisture, is converted to rust. And rust is basically iron 3 oxide. So these are showing you basically the different reactions that are taking place, or I should say half reactions taking place when iron is undergoing oxidation to form rust. So what happens first is that the iron over here in this equation is converted to iron 2 plus by oxidation, and then the iron 2 plus is undergoing further oxidation to form Fe3 plus, and it's the Fe3 plus that basically reacts with the oxygen from the atmosphere to form rust, which is shown here, all right? So that would be, those two combined would be basically the anode reactions. And then over here we have the cathode reaction, where the electrons that are produced at the anode will cause the reduction of oxygen to form water, all right? So that's basically the reaction that is taking place when it comes to iron undergoing oxidation to form rust. Now, if you have something made up of iron and you want to protect it from rusting, you can do that by attaching what is called a sacrificial metal, all right? Now, in this particular setup here, let's say you have an iron storage tank that you want to protect from rusting. Then what you can do is attach it to something which is more electropositive than iron. And in this case, that is the magnesium, right? So what's going to happen is that the magnesium, instead of the iron, will undergo the oxidation reaction which the iron would normally undergo. And the reason why is that if you check out the standard EMF values for the oxidation of magnesium compared to the oxidation of iron, you'll find that the EMF of the oxidation of magnesium is higher, all right? So therefore, between those two oxidation reactions, the magnesium oxidation is the one that's most likely to occur. So that's what happens here. So the electrons from the magnesium will basically be transferred to the iron storage tank, and those electrons, instead of the electrons from the iron, will cause the reduction of oxygen to form water, right? So in some textbooks, they call this the sacrificial use of magnesium to protect the iron. Another term that is used is the cathodic protection of an iron storage tank, because the magnesium in this case is basically responsible for the protection of the iron tank. All right, so that's basically it as far as the application of what we learned to the protection of iron. Okay, so that's it for this video. The next video will deal with electrolysis, and that's it for today. All right, take care.